Hey everybody, I'm in the lab today, so I got gloves on. My voice is probably echoing from the lab that I'm in. And I got goggles on because when we work in the laboratory, we always need to wear goggles, that's for sure. And when you get back to school in the real world, probably gonna wear gloves for a while too. Today, we're gonna focus on an experimental parameter that we can determine, and there are also tabular lists of what density is. So we're going to begin with just briefly discussing a little bit about what a sample's density is. So I wrote some notes up here, and I'm going to go over it and go over a couple sample calculations, go over how we can determine the density of a subsample of matter experimentally. So density is defined as an object's mass divided by its volume. And typical units that we use for this property, this characteristic, is grams per milliliter, or we can also report this and it would have the same numerical value, grams per cubic centimeter. And the reason why this would have the same numerical value is that 1 milliliter is defined as 1 cubic centimeter. So if anybody ever saw a hospital TV show, or if you work in a hospital and you need to give a patient 5 cc's of a particular drug, what you're actually giving them is 5 cubic centimeters, which is also equivalent to 5 milliliters of that particular drug. Now, density is an identifying property of a sample of matter. For instance, water has a density of 1 gram per milliliter or 1 gram per cubic centimeter at 4 degrees Celsius. So density does depend upon temperature, and that's due to the volume in the denominator of that particular property of density. Well, what's important about density, it depends upon temperature, but density is what we call an intensive property. Intensive. So in class, Dr. Albu probably discussed a little bit about properties in terms of intensive and extensive. Intensive, I always underline the IN. Intensive is independent of the amount. Another property, other types of properties are called extensive. An extensive property depends upon the amount. So let's begin with some extensive properties. Well, if we think about density itself, density is a ratio of 2 extensive properties, mass and volume, both extensive properties. If I have 50 grams of water and I add it to another 50 grams of water, the total mass is now 100 grams. Depends upon the amount of the sample that we're looking at. Extensive property, or an intensive property, intensive. Think about another one, temperature. Temperature is an intensive property. If I took 2 beakers of water and they were both at 25 degrees Celsius and I combined them, is the temperature going to change? Not really, it's still going to be at 25 degrees Celsius. So temperature is an intensive property. It's independent of the amount. Now, density is a property that depends upon 2 extensive parameters. Density is an intensive property. both mass and volume, if we increase the mass of a substance, we're going to increase its volume, and the ratio of those two are going to remain constant. And so density is an intensive property. It's independent of the amount of sample that we're looking at. So, ethanol. That's a kind of alcohol you drink. Don't go out and buy any if you're under the age of 21. But ethanol, it's ethyl alcohol. Ethanol, it has a well-defined density. It has a density of 0.789 grams. Let me write the 9 better, 0.789 grams per milliliter at 20 degrees Celsius. So at room temperature, that's the density of ethanol. Just write that as density E. So regardless of whether I have a cup of ethanol, so there's a cup of ethanol, wet your whistle with that, you got a cup of ethanol, that's ethanol in a cup. Or you go to some party and they have a swimming pool full of ethanol. Here's our swimming pool, here's our diving board, and there's people swimming back and forth in the alcohol, probably drunk. So this is a swimming pool. So if we have a cup of ethanol, here's our cup, and here's a swimming pool full of ethanol. If we're at 20 degrees Celsius, normal room temperature conditions, the density in the cup is 0.789 grams per milliliter. The density of the ethanol that fills that swimming pool, 0.789 grams per milliliter also. So regardless of the size, the density is the same. It's an intensive property. It's independent of the amount. Just lost a little light, but I think it looks better. Density is an important property that we can use in lab applications. Oftentimes, we're going to be getting reagents that are liquids, but a procedure might ask us for a mass of it. We could go over it and weigh it out. Problem with ethanol, if we needed to use a mass of it, let's just make up an example. What if we're going into lab and our procedure asks us to use a mass of ethanol of 10 grams? Well, what's probably easier to measure, it's in a liquid form, is to measure out its volume. We have better glassware that can do that. The mass of ethanol, to weigh that out on a balance, might spill some, might take some time. It might evaporate, and the mass might be changing. So what we can do is, since we know the density and we know the mass that we want, we can rearrange our density equation. Remember, density, D, is mass over volume. M is our mass, V is our volume. If we need a mass of 10 grams, we can easily weigh out a certain volume, measure out a certain volume, not weigh it out. And we can figure out the volume by rearranging our density equation. All we're going to do is cross multiply. The volume of the ethanol that we would require is equal to the mass over its density. Now, a lot of reagent bottles have density written on them. So we would treat a written amount of density on a bottle as an exact value. It's somewhat like a conversion factor. So if we're using a listed density, it wouldn't limit us in the number of significant figures that we would report. So let's calculate our volume. Here's our mass, 10 grams. Here's our density, 0.789 grams per milliliter. If we take 10 and divide it by 0.789, and I would use 4 significant figures. Let's treat the mass as our data. And we're going to say that's what's going to limit our significant figures. We would require 12.87 milliliters. So this is a good example of how we would use density to calculate a volume, and for liquids, those might be easier to measure than a mass that's asked for us. In other words, if we measure out 12.87 milliliters of ethanol, that's going to have a mass of 10 grams. And we would know that because we would know its density. So that's the use of density in an application. What if we were just wanted to determine a sample's density? What if we didn't know what a sample was, an unknown object? So let's think about determining density. To determine a sample's density, we could do it experimentally. We could weigh the sample's mass on a balance. We could do that in the laboratory. We can weigh its mass on a balance, and we would get a certain number of grams of our sample. And then we can determine its volume. So this is our first step. We need the mass, and we would need the volume also. There are 2 ways we can determine a sample's volume that we're going to be discussing. One way is by the shape of the sample. If the sample has a known shape, that we know the geometry of it, we can calculate its volume. And there are 2 types of shapes that we're going to be discussing. One is a cube. A cube has exactly the same length sides. And here's my artwork. Not too bad. There's a cube. It's a perfect cube. All the sides have the same length. L is its length. The volume of a cube is taking the side of that length and cubing it, raising it to the power of 3. So, remember what I said earlier? The volume 1 milliliter is equal to 1 cubic centimeter, and that's how we define the milliliter and get to our definition of the liter. If this cube has a side edge of 1 centimeter, then this cube has a volume of 1 cubic centimeter, and it also has a volume of 1 milliliter. So that's one particular geometry that we're probably familiar with. So again, we would know its mass. We also have another shape that we might be familiar with. And that's the volume of a sphere, spherical object. If I can find a marker that writes, we can talk about it. Hopefully this is a winner. It's not bad. Volume of a sphere. Losing more lights. It's looking better though. I think that glare was not too good. The volume of a sphere. Again, this is information you could probably look up on the internet, textbooks, whatnot. Volume of a sphere. Now a sphere, it's a circle. Sort of like that, but it's three-dimensional and it has like, the volume of a sphere, if you took maybe like a geometry class, a sphere looks sort of like that, with shading on it. The volume of a sphere is defined as 4/3 pi r cubed. And in this definition, pi is a number that you may be familiar with from a former, math class. Pi as a value. Pi is 3.14, and it has a lot of trailing digits. So if you use pi in a calculation, don't just limit it to 3.14. That's going to cause rounding errors. R is the sample's radius, the sphere's radius. Often it's easier to measure its diameter. Radius is equal to the sample's diameter divided by 2. So those are that's another shape that we should be familiar with. So let's go over a simple example of measuring a sample's mass and then using this formula here for a sphere and determining its volume. Because once we know the mass and we know the volume, all we got to do is take the mass over the volume, and the ratio of it's going to be its density. So hold on a second, I'm going to get my sample. That's a styrofoam ball. You're going to be seeing me use these. I use these for my geometry discussions, and they're useful for helping us identify atoms and how they're arranged to make up molecules. And I have it on a stick. It looks sort of like well, wherever you imagine you can. I got that there purposely because what I'm going to do is I'm going to determine the density of the styrofoam. I looked up the density of styrofoam, and what I found, it's somewhere around 0.045. So I want to see how close we can get to that experimental value. So the reason why I have the stick in here is I'm going to use this to measure its diameter. So we're going to be keeping this right here. And I'm going to measure its diameter by putting this stick in here and then putting a little mark on the stick. So I'm going to use this as a measurement. So if I put a mark on that stick, okay, if you can see, I put a mark on it. And then I'm going to pull out the stick. And you can see I have the mark on it just like that. And I'm going to use my trusty ruler right here. This is a ruler, if you can see it, in centimeters. And what I'm going to do is place this on the stick so you can see how we can measure this on our centimeter scale. So I'm putting the end of the stick at the very end. And I want you all to look at it. Trying my best here. Do we all see that? Okay. Look at it carefully now. Y'all got that? You can stop it. You can look at it later. But let's take a look at this little exercise so we understand a little bit about significant figures too. We did this exercise earlier. So I'm going to look at this real carefully and write down what I saw. You can write this. You can verify with when you look at this video. So if we looked at that ruler that I had, it had scale markings. We were a little over 6 centimeters. And this was the stick that I had that represented the diameter of that sphere. And if I look at this carefully, I noticed that this was 6.5. And then this was 7. So this is 6. And if we looked at this, and you can, again, look at it carefully later if you want, I would estimate 6.5, 6, 7, 6.8, and I'm going to go 6.81 centimeters. Again, somebody else might estimate it at 6.80, someone else 6.82. That last digit is our digit of estimation. So that's the diameter of that styrofoam sphere. So that's the diameter. Let's put that into our formula here and calculate the volume for that particular piece of styrofoam. So I got 6.81 divided by 2, and I'm going to plug that into my formula. 6.81 divided by 2, it should be like 3.4, or 3.4. 6.81. 0.05. Let's keep all of our digits. When we're doing our steps, we don't limit our digits between steps. 3.405 centimeters. So that's 6.81. So my radius, I'm going to plug that right into here. My radius is 3.405. Cubed. Okay, now we can plug this into our formula and calculate the volume for that styrofoam. So I got 3.405 raised to the third, multiplied by pi, times 4, divided by 3. I got 165.36, and I'm going to limit myself to 3 significant. Let's keep it. Let's keep up our data. 165.3636 cubic centimeters. 165.36. 151. And that's going to be in cubic centimeters. And remember, that would also be 165.3636151 milliliters. Good so far? We need its mass. We need the mass of this guy. Here's my styrofoam. We're going to go over to our balance. I'm just going to move this over here. We got a lot of light over here. This is pretty cool. So let's see what we got. We got a balance right here. So this is the balances. This is the type of balance you would use in the laboratory. This one's a top loader that actually has a little lid on it. And the reason why we have the lid, it prevents air currents from getting in there. The balance pan itself is sensitive to air currents that lift it up, and we don't want that to happen. What I'm going to do is put a weighing dish on here. There's the weighing dish. Got gloves on, which are important. I'm going to put the weighing dish on there. And if you notice, the balance starts to give us a mass. The mass of that, let's put the lid back on to reduce the effect of air currents. Now, all I'm going to do is simply tare it. Tearing the balance sets it to a mass of 0 grams. So basically we're setting it at 0 by tariffing. Now it's at 0. Now we're going to take our sample, put it on the dish. I put it on the weighing dish itself. And I'm not going to be able to use that because it's going to crush and push it down even further. So this is blocking it pretty well. I have a mass 6.4. Notice there's some deviations in the last digit. 6.442, 6.443, and that's the air currents. Let's go with 6.4. 6.45, 6.44. We'll go with 6.448. Everybody good? 6.448 grams. It's stabilized. 6.448 grams. Back to our data table. So 6.448 grams is our mass. Oh, that marker's not that good. 6.448. Okay. So just remember this limited us here. This radius was 6.81 centimeters. We're going to limit our final answer to 3 significant figures. And let's calculate the density. Are we all good? Density is equal to the mass that we've determined experimentally, 6.448 grams, divided by our volume, 165.36 151. And that's cubic centimeters, or that's an equivalent way of expressing it in milliliters. Means the same thing. Cubic centimeters and milliliters are the same unit. Essentially, it's measuring the same volume. So let's put this into our calculator. 6.448 divided by 165.3636151. And I got 0.03899. And if I was going to limit myself to 3 significant figures, the data that I looked up said it's about 0.045. Not too bad. Not too bad. Experimentally, what may have happened when I poked in that rod to measure the diameter, may have lost a little mass. And if the mass is a little less than what we wanted, then that's going to mean that our density should be a little higher since we lost a little mass. So pretty good. Not too bad. Not too bad. So that's one way of measuring the volume using the dimension of the sample. Another way of measuring volume, and this is often the case for irregularly shaped objects, is using water displacement. So water displacement is another experimental way to measure volume, and we would go and measure its mass using a balance. So water displacement. Let's define what we mean by water displacement. We can measure density. Remember, it's mass. Mass we can measure on a balance over volume. And an alternative way of measuring volume is what we call water displacement, H2O displacement. Okay, so what this method involves is taking a sample of water, and it's often conducted in a graduated cylinder in our labs, but in the simulation that you're using, it's this big trough of water. And we would measure the level of where the water is in a graduated measuring flask or device, a cylinder, for instance. And we would read the volume by recognizing the bottom of this curved region of our water, and in this cylinder is called the meniscus. So this is our meniscus. And we look at the bottom of the meniscus and where it sits versus our graduations on our measuring device. So what we do is we read this. And normally in graduated cylinders, not normally, but in all of them, we read volume from bottom upward. So in a 20 milliliter graduated cylinder, well, let's use 25. I believe that's the one we're using. 25. Or I think we're actually using a 50. We got a 50. Awesome. So if this was a 50 milliliter graduated cylinder, I'm not going to put those decimals in there because we're going to look at the one that we're using, and I want to show you how we understand the number of significant figures we limit in this case. We would read this level. This here might be 10. This might be 20. This might be 30. This might be 40, and there's 50. It's not quite as graduated as I like. And we would look at the different scale markings on there and estimate between two of them where that place is initially. And we would measure our initial water volume. I'll make up a number for this example. We're going to do a real one. What if I read that and I got 42.25 milliliters? Okay. And then I added my sample, an unknown sample. Here's 50. Now notice what happens when we put the sample in there. It causes the water level to rise. The sample has to be below the water. Can't be floating on top. And I've already had a few people ask me questions regarding the simulation that they're doing. Now if we read our final volume, what if it's 47.62 milliliters? Notice the difference between the two is going to be due to the volume of the sample that we put in there. So the volume of the sample is equal to the final volume of water minus the initial volume. (47.62). Whoops. Minus 42.25. I got 5.37 milliliters. And what if we weighed its mass? And we got a mass (12.35 grams). The density of the object is equal to 12.35 divided by 5.37 and I got a density of 2.29. .299, and if I limited myself to 3 significant figures, that would be the density of the object. Now, we might be trying to figure out what this object is. What's its identity? If we had a table that listed densities, we might be able to identify what that object is based upon the samples that we have. I actually have another experiment here. Let's try it. So this is the idea. And the object that we have, I'm going to push this over here. Looks like a piece of candy, but I don't know what it is. It's not candy because it's something that's not candy. So there it is right there in front of my shirt. It's a sphere. I could measure it just like we did before, but as an exercise, let's measure its density by water displacement. So the first thing we're going to do is weigh its mass. Let's come over to our balance that we have our styrofoam on. Come over and we'll tare it. It's 0. We'll tare it. We can use this time. This is very helpful. Tare. Sometimes we got to do it twice. Tare. There it goes. Now it's at 0. Let's put our trusty sample on there. I put it on the balance on that same weighing dish, and I have a mass of 3.869, 3.870. Remember, there is some fluctuation in the last digit. Looks pretty stable, and that's because we have this lid on there and there's no air current. 3.870 grams. Let's write down on the dry erase board. Please don't get sick by me moving this around. I know it's 3.870 grams. Let's calculate or determine its volume by water displacement. Over to our graduated cylinder. So here's a graduated cylinder. A lot of bumping. I'm sorry about that. So there's our graduated cylinder. Now I'm starting out with 11 milliliters. So there's our graduated cylinder. Now, if you look carefully at it, I'll put this blue backing behind it. You could see that the volume is at it's pretty close to 11 mil. I'm going to look at it again. And the increments are in 1 milliliter. So when we have 1 milliliter increments, this isn't very precise. We can estimate to the 10th position. In other words, this is 11.0 milliliters. We're guessing the 10th position of the decimal. And let's put our sample in the water to see how much of it gets displaced. So here's our trusty sample. Gonna wipe it off a little bit. So we're at 11. Carefully, so when we put these in here, Normally, we're going to put them on the side and let them slide down slowly. We don't want to spill any water out, and we don't want to break the glass. So I'll hold this up, let everyone look at it. Put it on a flat surface, maybe. I'll look at it and tell you what I got, and then I'll let you look at it. I'm seeing 13.9. Some people might see exactly 14.0. Some people are seeing 14.1. There's some level of estimation. So let's let's just say 14.0. So the final volume is 14.0 milliliters. So our water displacement, $14.0 milliliters minus 11 milliliters means the sample itself has a volume of 3 milliliters. So we're going to limit our answer to these two digits here, 3.87 grams divided by 3.0 milliliters. The density of that object (1.29 grams per milliliter. And if I'm limiting it to two digits, 1.3 grams per milliliter. Normally, if we're working in a more sophisticated lab setting, you would have your milliliters measured to the hundredths position. The examples that I showed a few minutes ago, those were a little better, the graduated cylinders. Those would be the ones that you can measure to the hundredths position, not the tenths position. And there are graduated cylinders out there that give that level of precision. So these are just some examples of the types of measurements we make in the lab. It's really a warm-up exercise to learn how to use glassware, how to go through some calculations involving some measurements that you do in the lab. And the exercises that we have for you on the simulation, very similar. And I just hope everybody has a good time at it. If you have any questions, send me an email and we'll do another video. Thanks a lot. Have a great day.